Apologize, the last video was very long. This video hopefully will be a bit shorter. We're going to continue with our Markov chain definitions and concepts that are going to lead us into our MCMC techniques by the end of this. So if you haven't already, take a quick look through your notes, refresh yourself on some of the vocabulary we've seen, and let's get ready to add to that. So the next bit of notation we're going to look at is this notation F sub I n. And this notation is going to tell us the I we're used to, going from state I to state I. This F part, instead of having a P here, F means we're going from state I to state I for the first time in n steps. So in our probability notation, at state 0, we start in state I at time 0. Then, for the next n-1 steps, we do not pass through state I at all. Finally, after n steps, we pass through state I. So this, again, tells us the probability of returning to state I for the first time in n steps. Emphasis on first time. Okay, a couple more bits of vocab to go with this. If we sum that up over all n, so first time I return is in 1 step, plus returning in 2 steps for the first time in 3 steps, and so on, that gives us the probability of ever returning to state I. Then, if I look at the expected value of this, think of our usual expected value formula is our mu in a discrete case, the sum of probability that a random variable takes on value little x times those x's. That's what we have here, returning in 1 step up to infinity steps. Those are our little x's. And then the probability of returning for the first time ever in n steps. So just our expected value is mu I, the expected time to return to state I from state I. We get this mu I. Okay. A couple of extensions from this. If Fii is less than 1, then that state I is said to be transient. So let's think about that in plain English. Fii less than 1 means the probability of ever returning to state I is less than 1. So let me put that in English here. Probability of ever returning to I from I is less than 1. And in other words, we are not guaranteed to return to state I. The probability is less than 1. It's not a guarantee. So not guaranteed to return to state I. And just kind of a second observation to go along with this, 1 minus Fii would tell us the probability of never returning to state I. Okay, so transient tells us that we're not guaranteed to return to state I when we start in state I. Okay, transient, not guaranteed to return. On the other hand, recurrent tells us we are guaranteed to return to state I. This Fii is equal to 1. This can happen in a couple of ways. So again, maybe let me make the note here. We are guaranteed to return to I from I. All right, this can happen a couple of different ways. First way is if mu I, the expected time to return to state I, is finite. Okay, so in other words, we have a finite expected return time, and this is called positive recurrent. So we are expected to return, we are guaranteed to return, and in fact, the expected return time is finite. And then I know this seems kind of strange, but we could have mu II be infinite. So our expected return time is infinite. This context is called null recurrent. All right, this is not a class on Markov chains solely, so we're not going to get into a whole lot of details here. I just want you to have some notion of the terminology for when we get to our big theorem coming up. Okay, another interesting observation is these ideas of transience and recurrence are class properties. So any states in a particular communication class share this idea of they're all transient or they're all recurrent within a communication class. Okay, the next page, our next bit of terminology here is this idea of an ergodic Markov chain, and requires two things. First, requires aperiodicity, so that meant our period was 1, or the greatest common divisor of return times is 1. And it also requires positive recurrence. Okay, so remember, positive recurrence is that our return time to state I from state I, on average, is going to be finite. All right, next bit of information here is that if T is our transition matrix, then Pij, remember what that means, the probability of going from state I to state j in n steps, is simply the ijth entry of T to the n. So this is matrix multiplication here. So this is the important part here. The probability of going from I to j in n steps is just given by the entry of the matrix T to the n. Again, matrix multiplication now. So I have sort of a hand-waving proof, or not fully complete proof for that here. This is clearly true when n is 1. That's the definition of T. Our transition matrix tells us the probability of going from I to j in one step. What about if we let n be 2? So probability of going from I to j in 2 steps is a probability at time t plus 2 we're in state j, given at time t we're in state I. Now we have this idea that the property that Markov chains are stationary. So we could keep this general and just start at the beginning of the chain. If we start in state I, the probability of being in state j 2 steps later, same thing due to stationarity. And so we have to consider, where are we passing through on step 1? Okay, what happens in between? So this probability is the same as, again, think total law probability, adding up overall the different options for stopping through on step 1. We'll call that K, and go add it up through all the different states in our state space. This guy is equivalent to, in state 0 starting in state I, state 1 going to state K, and then if we're in state K for step 1, moving to state J in step 2, this is just entry Kj from our transition matrix, Pkj. This guy is just entry Ik from our transition matrix. And if you think about matrix multiplication, I don't know if anybody else did this, but I've got my left hand going over, my right hand going down, kind of going across the row and column, adding those guys up. That's what this is. It's the ijth entry of T squared, matrix multiplication. So then our proof will follow through induction. Okay, but again, the important result here is going from I to j in n steps is just the ijth entry of our matrix T to the n. So let's check out an example and see what happens. So if you have R, you might want to pull that up and kind of pause and work in R as we're going through this. So the first thing, to define this transition matrix in R, I'm just going to call it MT, matrix T. Be careful of using lowercase t because that's a function in R for transpose. So I'll call it matrix T, and I'm going to use the function matrix. The first input is your elements of your matrix. So I'm going to give 0.7, 0.3, 0.4, and 0.6. Tell it the size of your matrix, so 2 rows by 2 columns, and I'm going to say n row equals true. So I've got, or not n row, excuse me, by row is true. Otherwise, it will think you entered this by columns, 0.7, 0.4, 0.3, 0.6, which I did not do. So I've got my vector. It should be formed into a 2 by 2 matrix. I entered them across the rows. Okay, so you can do that in R. Take a look at what the matrix looks like. Pause and do that if you need to. And here the question is, let's explore Tn. So if I want to find T2, then that would just be our matrix T, our transition matrix. And we're going to use this percent notation here to say, hey, R, don't do element-wise multiplication, but let's do matrix multiplication. So this will be matrix multiplication, our matrix squared. And if you do that in R, you're going to get this for your result, 0.61, 0.52, 0.39, and 0.48. Notice the rows are still summing to 1 in here. So this matrix is telling me the probability of going from state 1 to state 1 in 2 steps is 0.61. The probability of going from state 1 to state 2 in 2 steps is 0.39. And I could keep exploring this. I could find T4. If I did that, I would get something like this, 0.5749 and 0.5668. And then the second column, I've got 0.4251 and 0.4332. Again, rows still sum to 1. Maybe pause the video, try this a little bit more for higher powers of n, and see what you get. All right, hopefully you've paused, tried this in R a little bit on your own. I went up to T to the 8th, and I got something like this, 0.5715 and 0.5715 for my first column, 0.4285 and 0.4285. All right. That's kind of cool. What do you notice? Hopefully it's obvious. The more steps we take as n increases, we notice this trend happening. We are going from our original transition matrix, from transitioning from one state to the next in one step, to something that seems like the columns are converging. What does that mean? Think about this. This is telling me, you know, in 8 steps, the probability, if I start in state 1, my chances of going to state 1 are 57%. If I start in state 2, my chances of going to state 1 are also 57%. So after a lot of steps, who cares if I start in state 1 or state 2? My chances of being in state 1 are basically the same. Same thing here. My chances of being in state 2 after 8 steps are the same regardless of where I started. Okay, so this observation brings us to our important theorem here that's going to pull together a lot of the concepts and vocabulary we've been working on. So we need this idea that we have an irreducible ergodic Markov chain. So let's break that down. Remember our vocabulary. Markov chain, we needed stationary transitions. So it doesn't matter where you are in the chain, your chance of going from one state to the next is the same. We also needed it to be a Markov process, meaning going from one state to the next forgets the entire history of where you've been. It only matters where you are. So that's the Markov chain part of this. Then the ergodic part of it we had a moment ago was telling us this is aperiodic. So the greatest common divisor of going from one state to the next is 1, and positive recurrent. So meaning the expected return time is finite. Expected return time is finite. And then finally, irreducible. All of our states communicate with each other. So if we have all of these things happening in our Markov chain, then we can say that this value pi j exists. Not only does it exist, it's a unique solution to this system of equations. So pi j tells us is the limiting probability from starting in state I and ending in state j in n steps as n goes to infinity. So notice the observation here, the comment, this is independent of I. We're calling this pi j. So who cares what I is? The limit of this doesn't depend on I. It doesn't depend where we start. So that's exactly what we kind of observed in our little toy example here. It doesn't matter if we started in state 1 or state 2. The probability of ending up in state 1 is the same. The probability of ending up in state 2 is the same, regardless if we started in state 1 or state 2. Okay? So it exists, and it's independent of where we started. Also, it's unique, and specifically, it's the unique solution to this system of equations. So pi j is the sum of the pi ij times pi I over our state space, the i's in our state space. And then, of course, all these pi ij's have to sum to, or pi j's have to sum to 1. Just like we observed here, the rows have to sum to 1. So like this would tell me my pi 1 is 0.57, my pi 2 is 0.4285. All right, let's see if we can actually use this theorem in our particular example. So in our example we were just working on, we had T was our transition matrix, 0.7, 0.3, and our second row is 0.4 and 0.6. Pi is this stationary distribution, pi 1, pi 2, and I kind of glossed over that here in the notes, our stationary distribution in the Markov chain, and that tells us regardless of where we started, state 1 or state 2, the probability of ending up in state 1 or the probability of ending up in state 2 after a long, long time, this is the vector that tells us that. Okay, so if we kind of break down our system of equations here, I only have 2 states in our simple example. So pi 1, pi j, we'll start with j equals 1, is the sum of pij, so over the I, so I'll start with I equals 1. So p11 is 0.7 times pi 1 plus, now I is going to be 2, so p21, so that's this guy, 0.4, times pi 2. Then I have pi 2 is equal to p12, so this guy, 0.3, times pi 1, plus p22, so 0.6 times pi 2. And of course we also have that pi 1 and pi 2 must sum to 1. Okay? Most of you guys are math majors or have had enough math. You can solve this system of equations. So I'll kind of skip over that step. And you get this vector pi 1 is equal to 4/7 and pi 2 is equal to 3/7. If you kind of approximated those with a decimal, you get 0.57143 and 0.42857, which is really cool, not surprising because of what we observed over here. So this stationary distribution, again, is telling us if we run our chain for a long time, moving from states to state, according to our transition matrix T, we're going to end up in state 1 with probability 4/7, state 2 with probability 3/7, regardless of our initial distribution, regardless of where we started. Okay, so now we're going to put this into context that we'll use in the next unit. So the idea is we have a similar theorem if we have a continuous space Markov chain. So all our definitions have been in the finite discrete case just because it's easier to understand. But if you translate all those ideas over to continuous space Markov chains, we have this the same theorem, and it gives the existence of a unique stationary distribution, F, and this distribution is a PDF now. So instead of a vector of discrete points, now we have a PDF, F, and instead of a system of equations, we've got our expression here. So F, this is our stationary distribution. Same F right here. Stationary distribution, that's like our pi in the earlier example. The integral is like our sum in the earlier example. This T is like the PIJs, or elements for the transition matrix in the earlier example. But here, think of this as a transition density. Okay, so it's a distribution that's going to tell us the probability of starting in some value in set X and moving to some value in set Y. And we have the property that the integral of Tx y over the y's should be 1. Y's in the state space, which is continuous here while we're integrating. So that's like saying if I start in a particular state X and I sum or integrate over all the different places I go, I should get 1. All right, so why is this important? Why is this really cool? So we've mentioned that we're often going to have really complicated problems, really complicated distributions. So in the next section, our target distribution is going to be the stationary distribution F, some really complicated distribution F that we have no method for sampling from. Okay, but there have been several different techniques developed to construct a Markov chain, define this transition density, so to speak, where we're guaranteed to converge to that stationary distribution of interest. And why is that important? If we can generate samples or get probabilities associated with this stationary distribution, then we know a whole lot. We can do all kinds of inference if we can gather samples from the stationary distribution. Think about the things we did in the last section. We can come up with confidence intervals for parameters, for example. So in the next sections, we're going to be looking at techniques for generating Markov chains that are guaranteed to converge to this unique stationary distribution. Two of those methods that we're going to look at called Metropolis-Hastings and Gibbs sampling. And if you remember, Metropolis should sound familiar. Metropolis was Nicholas Metropolis, who is a colleague of Ulam and Newman. We're working on the hydrogen bomb. He was the one that suggested Monte Carlo is the code name for the Monte Carlo techniques. Just a little heads up, Metropolis-Hastings, often used in univariate settings, doesn't have to be. Gibbs sampling is clearly used for multivariate settings. So we'll see examples of both of these in the next unit.